Welcome back to aerodynamics class. Today we will be discussing about airfoil nomenclature, right? So airfoil becomes a very important part of our aerodynamics class, right? Aerodynamics course. So we will start with the airfoil nomenclature because hereafter we will be discussing many things, which will be like support the theoretical aerodynamics, and hence knowing about the airfoil is very important. Hence we start. So I acknowledge fundamentals of aerodynamics by John T. Anderson. So you might have already studied the airfoil, right? So you know about the airfoil. So yeah, an typical airfoil looks like this. So I recommend everyone to draw the airfoil in your notebook, maybe many times, right? So you should practice drawing the airfoil. And here you have a free stream velocity, V infinity. And in this airfoil, say we will have a leading edge. This is a leading edge, right? So I will write here. It is a leading edge. And this is a trailing edge. And the shortest distance which joins the leading edge and the trailing edge, right? So the shortest distance which covers the leading edge and the trailing edge is called chord line. So usually we say chord C, right? Right? Now, if we want to say thickness of the airfoil, right? We say this is the thickness. Right? Then we will have another line. Say, for example, you have one point here and another point here, and we can note the midpoint somewhere here. Similarly, the upper surface and the lower surface, we can mark the midpoint. And here I mark the midpoint. So I mark this particular line, which is the line joining the midpoint, right? So this line is called mean camber line. Mean camber line. Right? So the maximum distance between the mean camber line and the chord line is called camber, right? I mark this as A, and A is a camber line. You can say camber, mean camber line and camber, right? So usually the definition of camber is the maximum distance between the mean camber line and the chord line measured perpendicular to the chord line, right? And again, the definition of the camber line, mean camber line, right? We have drawn a mean camber line. So we can say that mean camber line is the locus of points halfway between the upper and the lower surface as measured perpendicular to the mean camber line itself, right? So we have the camber line and the chord line. And as usual, you know very well the angle between the chord line, right? So I write this here. The angle between the chord line and, say, if this is the chord line, if this is the airfoil, and this angle is angle of attack alpha, right? So we know this angle of attack alpha. Now we have 2 points. One is infinite wing and finite wing, right? So let us start with the infinite wing, right? Say infinite wing. What is infinite wing? Any idea? Anyone can say what is infinite wing?
Wing with infinite span.
Wing with infinite span, right? Say I would like to draw one wing. So this is the wing. Okay. And can you imagine this is a wing? The plan view, and this is the side view, right? And this is the chord line, C, and this is the span area, S, and this is the span length, B. So span area is equal to B into C. Now, the infinite wing, we say, is not the infinite geometry of the wing. Instead, say in this particular wing, the flow is from here, say V infinity. Now, if you take this particular section, say 1, and this section 2, this cross section 3, this cross section 4, and this cross section 5, and another cross section 6. 6 is the cross section very much near the tip of the wing. Now, if you say at point at the cross section 1, cross section 2, 3, if you see the behavior, say the surface pressure behavior will be same. And I can say that what 1, 2, 3, 4 also it is same. Maybe at 5 or 6, there may be an influence from the bottom surface and the top surface, right? So if I keep an end plate, say I keep an end plate, here is an end plate, right? So to have more imagination, I will do one thing. I will draw the end plate, right? This is one end plate, and you have an airfoil you have a 3-dimensional airfoil fixed, right? And you will be having another end plate here, right? You have airfoil. And this airfoil is fixed at both the ends. Assume that we have a wind tunnel. It is in the wind tunnel test section. So if this is this is the case, every cross section you will have the same aerodynamic property, and hence this wing is called infinite wing. Means that in the infinite wing, right? In the infinite wing, there is no change in the aerodynamic property with various cross sections. Now you may ask, sir, then where there is a difference? So I can say something called a finite wing. Right? So this is my wing, right? Now I leave a city and the end plate, another end plate is here, right? So if you see in the top view, it will be like this. And I say that the free stream velocity is here. Now what happens? Because of the pressure difference, the high pressure region here and low pressure region here, if you keep it at some angle of attack, the high pressure region tries to come to the low pressure region, right? And it forms an induced drag that you already know. So this creates a difference, and all these location you will be feeling a different aerodynamic characteristics. Hence we call this as a finite wing. Assume that you keep on say if this is an end plate and you have a wing and you are keeping a winglet, you know winglet, right? If you keep a winglet, the properties here again changes. So this becomes finite wing. In infinite wing, the flow is, you have a flow, and one can say that the flow is there in x and y direction, and hence flow over an infinite wing is 2-dimensional. Now, in the case of finite wing, I said there is a flow in the 3rd dimension also. So flow over a finite wing is 3-dimensional. Right? So these are all some information on the finite wing and the infinite. Okay. In John D. Anderson, in general in aerodynamics, if I say CL or CD, it corresponds to the 2-dimensional geometry, and this is for airfoil. But if I mention C and capital L on C capital D, then it is the characteristics of a wing, which is in turn 3D, right? So this is the convention most of the aerodynamists follow. So please note this. Okay. So we will move to the next point. Airfoil nomenclature. We have a nomenclature of naming the airfoil, right? So we usually name with 4-digit, 5-digit, 6-digit series, and we start with NACA. What is NACA series? What is NACA? Somebody know NACA? What is NACA? Yeah, anyone? You forgot? Most of you might have read about NACA in the introduction to flight.
National Advisory Council for Aeronautics, the previous thing of NACA.
Yeah, National Advisory Committee for Aeronautics, correct? So we have NACA series, say 4-digit airfoil, 5-digit airfoil, and 6-digit airfoil. Right. So there are many NACA series. So for example, if I say NACA 2412, it is to define an airfoil. What it means is the last 2 digits, right, stands for the maximum thickness. You know the thickness now. So it means that percentage of maximum thickness. So the maximum thickness is 0.12 times of C. So here you have C, and 1-2 times of C is the thickness, right? 0.12 times, that is 12% of the chord, is the thickness. Second point, this 4, right? This 4 notes that the maximum thickness lies at 0.4 C, right? 0.4 C lies the maximum thickness T. Usually we write thickness as thickness to the chord ratio, right? So maximum thickness lies at 0.4 C. What is 0.4 C? One can have a mind calculation. This may be 0.5 C, and this may be 0.4 C. Some case it may be 0.3 C, right? So the location of the maximum thickness is at 0.4 C. What is 2? The maximum camber is 0.02 C, and it is located at 0.4 C from the leading edge, and the maximum thickness is 0.12 C, right? Now there is exercise NACA 0012. Now the question is whether it is a symmetrical airfoil or unsymmetrical airfoil. Or unsymmetrical airfoil. Right? We know if this is the chord line and the airfoil is symmetrical about the chord, or in the other case, you have a airfoil where the airfoil is not symmetrical about the chord. So this is a symmetrical airfoil, and this is unsymmetrical airfoil. Right? Now tell me, NACA 0012 is a symmetrical airfoil or unsymmetrical airfoil?
Symmetrical.
How it is symmetrical?
In symmetrical airfoil, mean camber is 0
Yeah.
because it coincides.
So this has 0.12 C, but the thickness maximum camber is 0. There is no camber, right? And the location at the maximum camber is 0. So this is a symmetrical airfoil. Okay. Similarly, I want you to look for 5-digit and 6-digit series and learn about it. Okay. Now we will have certain characteristics of the airfoil. Okay. So I will try to draw the lift curve. Right. So in the lift curve, we have angle of attack alpha, and in the y-axis, the right CL. Right. Now, one can draw the lift curve slope. So I will draw like this. Similarly, I can draw another curve. Right. Now, say this is A and this is B. What is A and what is B? Anyone can say? What is A? A corresponds to which airfoil? Okay.
Symmetrical, B unsymmetrical.
Yeah. So A corresponds to symmetrical airfoil, right? So this is the point CL max, right? So what is this point called?
Stalling angle.
Yeah. So this point alpha is alpha stalling, right? So what is really happening at the stalling? You have the airfoil at a particular angle of attack where you have a flow separation occurs, right? And it creates enough weight, and since there is a flow separation, there is enough weight, the lift starts decreasing, right? And in general, the drag may be increasing, right? Okay, so this is the stalling. So stall, I can say like stall due to flow separation. Right. So one can write the slope. Say I write the slope like this. I draw the slope of the curve. So I can write this is BCL and this is the alpha, and one can write the slope as A naught is equal to BCL by D alpha. that is equal to lift curve slope. Now, at angle of attack alpha is equal to 0. Here is the point where the angle of attack alpha is equal to 0, right? So, at the angle of attack 0, there is a 0 lift. That is for which airfoil?
Symmetrical.
Yeah. So, it is called 0 lift angle of attack. Okay. 0 lift angle of attack. Usually we write like alpha at L is equal to 0 is equal to 0. So this corresponds to the symmetrical airfoil, right? Okay. Now, what happened at CL here? Now here also the CL is equal to 0. What about the CL equal to 0? Here? So for for unsymmetrical airfoil, alpha at L is equal to 0 is equal to what? We have written alpha L equal to 0 for symmetrical airfoil. Means that angle of attack is 0 when L equal to 0. Now the angle of attack at L equal to 0 for unsymmetrical airfoil, what may be the value? At least for this case. So assume,
negative value.
yeah. So this may be negative. Okay. So it all depends upon your camber, right? If your camber, if you have an airfoil like this is having a positive camber. Now, what will happen if I have an airfoil like this? So what will happen in this case? It may not be negative, right? Okay, good. So we have the lift curve slope, which discusses about the 0 lift angle, and then the stalling, flow separation, right? So we will have a detailed discussion on flow separation, right? Again, what is that the CL max corresponds to? CL max. What is CL max corresponds to? This is CL max. So CL max corresponds to what angle? Right? Anyone can say? CL max corresponds to what angle?
Stalling angle.
Stalling angle, right? Okay. So CL max corresponds to stalling angle of attack. Okay. Now, okay. So let us have a problem, right? This is very simple exercise. So we can have a problem, right? So please note the problem in the airfoil nomenclature. Right? Consider an NACA 2412 airfoil that we have already seen. 2412 airfoil having an chord length of 0.64 meter, right? And assume the standard sea level condition. What is standard sea level condition? So usually the standard sea level condition. What is the density at the standard sea level condition? 1.23. I will write 1.23 because to stop it in the second digit, right? So we have our O infinity at the free stream, and also we can write the mu, that is 1.789 into 10 power minus 5 kilogram per meter second, right? And know the free stream velocity V infinity is equal to 70 meter per second. The lift per unit span, do you remember lift per unit span is equal to rho infinity V infinity gamma. The lift per unit span is 1254 Newton per meter. Calculate the angle of attack alpha and drag per unit span. Calculate the drag per unit span. Right? So please note the problem.
I'm going present for the 3 days now.
So let us start with the calculation, right? So you have a lift per unit span, and we have L dash. So if you know L dash, you can calculate CL. 1254. I can count. So what is CL? Is L dash by Q infinity F. We can take. Right? So what is S? S is equal to P into 1, we consider, right? Unit span. So what is CL? So please calculate and let me know CL. Q infinity, you know very well, Q infinity is equal to of rho infinity V infinity square, and V infinity is already 70 meter per second, and rho is 1.225 kilogram per meter cube. So what is the value for CL? What is the value for CL?
So 0.65.
Okay. So 0.65. Okay. Now, I want you to look into the graph of NACA 2412 profile and the corresponding CL of 0.65. What is the corresponding alpha? So please look into the book. We have a graph which is drawn between CL versus alpha for this particular airfoil. Right? Then the second one, we need to calculate the CD. I mean, not CD, D. Right? So we already know that the CD, right? We remember in the last class we have drawn CD is equal to the function of Reynolds number. I hope you remember that. We have drawn the CD for a circular cylinder and the Reynolds number, and we have drawn something like this. So if someone knows the Reynolds number, the corresponding CD can be calculated. I mean, at least from the graph, we can understand the CD, right? So how to calculate the Reynolds number? What is the formula for O infinity, V infinity, C by mu? So what is the Reynolds number? So please calculate and let me know what is the Reynolds number.
So 3.07 into 10 power 6.
Okay. So 3.07 into 10 power 6. So we have a graph, standard graph for NACA 2412. I recommend you to use the John D. Anderson book and find for the Reynolds number of 3.07, maybe 3.1 or something like that, you can find the corresponding CD value. So by getting the CD value, one can calculate the drag per unit span. What is the formula for drag per unit span? Of rho infinity V infinity square S into CD, where you already know of rho infinity V infinity square is Q infinity, and the S is C into 1, and you know the CD value. So please calculate this by yourself, right? Use the John D. Anderson book or any other material to calculate the corresponding angle of attack value, corresponding coefficient of drag value, and calculate the drag per unit span. Okay. So I stop at this point for the today's discussion, right? Thank you very much.